guys, I'm Grant.
And I'm Elliot.
And today we're going to be talking about G.
That's acceleration due to gravity on Earth in a vacuum. Now some of you might be wondering, how can objects with different masses still fall at the same rate?
If heavier objects are pulled harder by gravity, then why don't they fall faster?
We can explain this using the equation Fg equals big G times m1 times m2 over r squared.
So the force of gravity acting on an object is equal to g, the gravitational constant, times the mass of the Earth, times the mass of the object, over Earth's radius squared. Now we know from Newton's second law that F equals ma. So the mass of the object times its acceleration should equal this force. But when we look at these equations, we see that the mass of the object can cancel from both sides. So therefore, the acceleration of the object is dependent only on g, the mass of the Earth, and Earth's radius squared. As we can see, the mass of the object doesn't matter and only depends on these other things, which are constant. But if all objects are supposed to fall at the same rate, then why does this happen?
Acceleration due to gravity is only constant in a vacuum. In real life, there's also upward force of air resistance in addition to the force of gravity, causing objects to fall at different speeds depending on their air resistance.
To mitigate the effects of air resistance, one thing we can do is reduce the force of air resistance by decreasing an object's surface area. Notice from A to B, the object gets skinnier and therefore experiences less friction with the air and less air resistance. Also, we can increase an object's mass to increase the amount of gravity affecting it. The force of gravity here is stronger compared to the F of air resistance, and therefore it's going to be more resistant to the air resistance as it moves down. We know from kinematics that the change in y is equal to the initial velocity times time plus a half at squared. But we know that when we drop an object from rest, that its initial velocity in the y direction is 0. So we can ignore this term. Then we can set change in y equal to a half at squared. Then all we have to do is divide both sides by t squared. And if we graph change in y over t squared, we'll get a half a.
Now that we have an equation that we can use for our experiment, all we need to do is get data to verify that this equation holds true. So if you can remember, we had a change of y and a t squared that we can actually measure in an experiment. So the change of y would be the varying heights that we would drop an object at. And you would need a partner who would take the time that it would take for the object to fall. So this would be one trial.
That took about 0.7 seconds.
High five! During your experiment, when you're dropping objects, you might want to take into account your partner's reaction time. A good way of doing this is by dropping your object at higher heights. That way, the total time taken for the object to drop isn't as influenced by your partner's reaction time.
You can also add or subtract the reaction time at the end, depending on how your experiment is set up. In some experiments, you might be able to see and anticipate the object hitting the ground, in which case you might not need to account for reaction time.
Hey Elliot, think fast!
To complete the experiment, keep dropping the object from many different heights and record the time it took for the object to fall. Then you can use the data to create a graph like this one, in which you have the distance the object fell on the y-axis and the time squared on the x-axis. Remember from earlier that delta y over t squared equals 1/2 a. This corresponds to the slope of our graph. Therefore, the slope of a best fit line of our graph should yield half a or half g.
Here are some review questions to make sure you understand the material.
Your first question. If a bowling ball and a feather fall from the same height in a vacuum, which one falls down first?
On a planet with twice the mass but the same radius, what's the acceleration due to gravity?
In real life,
Do objects fall with acceleration equal to g?
Thanks for watching.
Subscribe to Andres Aragoneses on YouTube.